Alrighty. So we talked last time we were talking about the multiplicity of a root. It's the number of times a root or a factor appears in the fully factored form of a polynomial. And so now we can have some kind of interesting dialogue about this. Let's look at this polynomial. For x to the 4th plus 3x cubed, right with my hand, minus 12x squared minus 52x minus 48. What we want to do is we want to completely factor this polynomial, knowing that the root -2 has a multiplicity of 2. All right, challenge accepted. So the root, remember, root is another word for a 0, an x value that can be plugged in here that will produce a 0 as a y value. So -2 might be the root, but remember, that's like saying x equals -2. And if I add 2 back to the other side, that's the same as basically saying x plus 2. So the factor will be x plus 2. But another thing we know is it has a multiplicity of 2, meaning it can be factored out of this entire expression 2 times. So what we're going to do is we're going to use synthetic division twice. We're going to use synthetic division to divide it out, and then we're going to divide it out again of the leftovers. Now, if this information wasn't supplied to you, you'd have to go about factoring this polynomial a different way. You'd really have to use the rational roots test and just go down a list of rational roots and just slowly get to factoring it. So it's pretty nice that this information is provided to us. So remember, for the synthetic division, we put the root itself, -2, in this upper left corner. Then we write out the coefficients of this 4th degree polynomial with some spacing in between. 1, 3, -12, -52, -48. There we go, nice spacing. Put a nice line here. And now we go about it. We bring this one down. -2 times 1 is -2. 3 plus -2 is +1 again. -2 times +1, -2 again. -12 plus -2 becomes -14. -2 times -14 is +28. And now we got to do -52 plus 28. We know it's still going to be negative, but then secretly we can come over here and do this side calculation. Borrow a 1. It's not really borrowing, it's taking. 4, that's a 4 minus 2. So we get -24 here, and it actually looks like things are going to turn out bright for us. -2 times -24 becomes +48. And so -48 plus 48 is that 0 remainder. Very good. So now we have a polynomial. It's going to be a third degree polynomial with these coefficients that is left over. So what we can actually do is something like this. Because we just did the synthetic division, all we need now are these leftovers. And what that says is that this fourth degree polynomial can be written as this. The root was -2, but the factor is x plus 2. So it can be written as x plus 2 and the leftovers would be a third degree polynomial, 1x cubed, so just x cubed, plus 1x squared, so just x squared, minus 14x minus 24. All right, so we've made some nice progress, but we've been told that this root has a multiplicity of 2, which means I can factor it again out of this cubic polynomial. So I can use synthetic division again, use -2 up here, and then I can do it on these coefficients here. I'm factoring out of this cubic polynomial. So once again, go down the line, bring down this 1, -2 times 1, -2. 1 minus 2, or rather 1 plus -2, which just becomes 1 minus 2, is -1. -2 times -1 becomes +2. -14 plus 2 becomes -12. -2 times -12 becomes +24. And then -24 plus 24 is just 0, which is the remainder. So now we've already factored out an x plus 2 that's already there. Now what we can say is that we're factoring out yet another x plus 2. And the leftovers is a quadratic polynomial, a second degree polynomial with these coefficients, x squared minus 1x minus 12. Thanks to the wonders of synthetic division. But we're still not done. However, we've really done all the heavy lifting at this point. We want to completely factor it, meaning we'd like each of these factors to be linear, where the highest power term is just a 1 on the x. This, however, is a quadratic factor. Now, it's not always possible that it's going to factor. So this could be completely factored, but it's not guaranteed. We need to actually investigate. So let's investigate. Let's see, can we factor? We're just looking at x squared minus x minus 12. Let's see, two numbers that multiply to -12, but when I add those numbers, I get -1. Oh, -4 and +3 will work. So this can be further factored. We have this x plus 2 here, but wait a minute, I'm even going to condense that. It's just the same factor appearing twice. And from what we talked about last time about multiplicity, we can just say that. X plus 2 squared. And then we already argued that x squared minus x minus 12 can be factored as x minus 4 times x plus 3. And now this is fully factored. This is as good as it gets right here. No better than that. And we're done. All right, not so bad, not so bad. Let's try out another example problem. Let's find, so this is an example, find a polynomial that has zeros of -7, +4, and 0, for which f of 2 equals 1. And we're using the word 0 interchangeably with the word root. So let's see, it has to have roots of -7. So it's got to have roots really of x plus 7. So that if I set this equal to 0, this factor equal to 0, I'd get -7. It's going to be x plus 7, x minus 4, and then you could put x minus 0 here if you were so inclined. Now what we're going to say is that this is going to be our function, we're supposing. It behaves according to all this over here. It has these roots. There's actually one other little fly in the ointment. You could actually put any constant you wanted here. I could put a 3 out here. And that's not going to change any of this. It's still going to be a polynomial, and it's still going to have roots of -7, +4, and 0. So I can actually put anything I want. I could put -4 if I wanted to, and it fits the bill for all of this. But there's this stipulation here. It says f of 2 has to equal 1, meaning if I plug a 2 in for x, it needs to spit out a y value of 1. So that means we need to figure out which constant needs to go right here that's going to produce this result. So what I'm going to do for now, I don't know what that constant is. I'm going to call it A. And I'm going to go ahead and figure out what that has to be. Now, another thing I'm going to realize is also, I kind of wrote it here just to drive a point home. But this factor x minus 0, when you subtract 0 from something, it doesn't change that thing. So instead of writing x minus 0, I could just write x by itself and be the same exact business. And it makes my life, it's going to make it a lot easier here, as we're going to see in just a moment. So now we need to figure out what this constant value could be. We need to figure out what it could be. So let's just impose the rule. F of 2 which means we plug a 2 for x into this business. So it's going to be A times 2 plus 7 times 2 minus 4. We're just plugging in 2 for x times 2. It has to equal 1. It has to be a y value of 1 whenever we do all that. And then what we're going to want to do is we're going to want to solve for a. So we really have like this equation here. And we want to solve for the constant a. So let's do the arithmetic. A, 2 plus 7 is 9. 2 minus 4 is -2. Times 2 over there needs to equal 1. A is the constant we don't know, so we need to just multiply these numbers. 9 times -2 is -18. Times +2 will give you -36. So this reduces to a times -36 equals +1. Now I would just need to divide both sides by -36 to get a by itself. So that constant ends up being -1 over 36. And so finally, the answer is going to be, well, this was the function written out. Now let's just substitute in a -1 over 36 to this. And so this is our polynomial. And if you were so inclined, you could FOIL out this x plus 7, x minus 4, get it to combine like terms, distribute through this x, and then distribute through this -1 over 36. But we don't necessarily have to do that. We can leave it in the factored form here, because that's just going to make our life easier. So we really just have more and more and more of these kinds of example problems involving polynomials, factors, things like that. Really, all of this is just a consequence of some of the theory we've been developing over the past couple of days, especially last class. And it just kind of keeps going and going and going. This is the longest section in the entire book that we cover. And it's really just a lot. It's a lot kind of thrown at you. So in that vein, let's continue on with another one. Let's see. Find the polynomial of lowest degree that has zeros/roots of so this one's going to be kind of interesting. We're going to actually have complex roots here. Complex roots involving I. And that's actually going to put an entire twist into it. Yes. And we're even going to say that the root of 3 that we want to bring into this needs to have a multiplicity of 2. It needs to show up twice in the calculation. Okay, so this is what it would have to look like. And what we're going to see is this is going to end up being quite the computation. There's just no two ways about it. Let's see. A polynomial of lowest degree which has these roots. Well, it's going to have to be x minus whatever the root is. But the whole root is 2 minus 2i itself. So it's going to have to look like this. Then we're going to have to do x minus 2 plus 2i. And that's just really the implied procedure here. And then we're going to have to go one further. In this root of 3, it's going to have a multiplicity of 2. It's going to have to show up twice. And so what we're going to see is that is the factored form out. We could have a constant here, but since it doesn't give us any guidance as to what that constant could be, we're just going to assume a constant of 1 over here. And we're just going to be happy with that. Now, technically, what we ought to do, we ought to fully multiply this polynomial out. And that's going to be a little bit of a pain if you ask me. And you are asking me because I have done this before. I think it is good measure to go ahead and multiply it out because we're going to see something magical happen. Notice that these roots are conjugates of each other. We just flip the sign in the middle between the i's. And whenever you have a root that are conjugates, you're going to see that you're actually going to have your i's cancel out completely whenever you do the factoring, or whenever you do the multiplying out. So we need to FOIL this. And we're even going to ignore this part for just a moment. We're going to need to factor this completely. So x times x will give you x squared. Then we're doing x times negative 2 plus 2i. So it's going to kind of look like this. And then we're basically doing minus 2i times x. And then we're doing negative 2 minus 2i times negative 2 plus 2i. Those negatives are going to cancel out. Like that. And now we actually still have some more work to do. And I'm sorry, there's supposed to be an X on that one. My bad. I even said it verbally, but I did not write it. And that came from doing X times that here. we're going to need to distribute everything out so we can drop parentheses. So we're going to get x squared minus 2 times x. We need to distribute the x. Minus 2i times x. So we've distributed out this one. Then we're going to do minus 2x again from distributing this subtraction with this x over here. Then it's negative 2i, so it's going to become plus 2i times x, this x here. And then finally, we have to FOIL this out right here. So this is just one little subset of the whole thing. We're going to have to do plus, let's see, 2 times 2 is 4. 2 times 2i is 4i. Negative 2i times 2 is minus 4i. Negative 2i times positive 2i becomes minus 4i squared. And while this looks really bad at the moment, look what happens. We have minus 2ix plus 2ix. Those are going to cancel out. Those are going to go away. I have plus 4i. I have minus 4i. Those are going to cancel out. Over here, I have minus 4i squared. And remembering that I squared is negative 1, this is essentially going to become plus 4. And then we had another plus 4 over here. Just collecting what's left here. We had minus 2x from here. We have another minus 2x. And then we have x squared at the beginning. So we actually kicked I right out of town by doing all of this. There's no more i's left in this. We're just left with x squared minus 4x plus 8. So all of that is actually pretty cool, because this means that this entire polynomial here, we can start factoring it or start simplifying it like this. Like this. And we still have this x minus 3 squared. But ultimately, what it means is that even though we had some roots, we had some zeros that involved I, that were complex numbers. The polynomial itself, if we were to fully multiply this out, would not have I involved in it. Which makes sense because we said that polynomials, they have to have only real number coefficients. You can't have a coefficient that has I involved. Thus, this wouldn't have been a polynomial if that didn't happen. The reason we actually got rid of the i's is because notice that 2 of our roots were just complex conjugates of each other. 2 minus 2i is just the conjugate of 2 plus 2i. Now, if I tried to throw in another root, or if I tried to make this, say, 5 minus 2i instead, and I didn't change anything else, that's going to be a problem because 5 minus 2i is not the conjugate of 2 plus 2i. And so when I actually go out to multiply everything, I'm actually not going to be able to get rid of my i's, and I'm just going to have I involved in it, which means it can't actually be a polynomial because then you're going to have coefficients that are not real, they're complex. So that's just clearly not allowed. So the big bottom line here is that anytime you want to have a complex number as the root of a polynomial, anytime that issue comes up, its conjugate is also forced to be a root, even if it's not explicitly stated to you, because that's the only way you're going to end up canceling out any i's and not having I involved in the final form of the polynomial. In fact, that concept is so important, it's a fundamental concept in algebra. And it's even got a fancy name called the conjugate roots theorem. So I'll kind of write it out formally. If f of x is a polynomial with a root of a plus bi, the root's complex conjugate, a minus bi, must also be a root of the polynomial. You can't just have it once. You can't just have one conjugate root. You have to have its partner, its sister, its conjugate as well. It's just not possible otherwise. This means that complex roots appear in pairs. You can't have one without the other, as Frank Sinatra once sang. So that's kind of interesting. There's actually a lot of, as we continue to learn more and more about all these different algebra concepts, we're going to actually see more reasons why this is forced to occur. This must happen. It doesn't make sense otherwise. So anytime you see a complex root in algebra, in a polynomial, its conjugate is also a root. Well, this means we could do something like this. Find a polynomial that has roots of -2 as well as 4 minus I and is of lowest degree. Okay, so let's analyze each of those. This means -2 is a root, which means that x plus 2 needs to show up as a root to that polynomial. It also has a root of x minus 4, so x minus, the root is 4 minus I. When we write it as an actual factor, it's going to be x minus 4 minus I. Now, it's not explicitly told to you. It is not told to you, but this is not done. This is not done. The conjugate roots theorem automatically forces 4 plus I, the conjugate of this, to also be a root, whether you like it or not. So even though it's not been explicitly told to you, this is impossible unless you also include x minus 4 plus I as a factor. So this is due to the conjugate roots theorem. It is simply the case whether we like it or not. Now, the other thing here, it says of lowest degree. What that means is don't get fancy with the multiplicity. Don't try to make this to the 4th power and this one to the 7th power and this one to the 7th power. Technically, you could do that if I didn't tell you it's of lowest degree. If I didn't say that, you could say that -2 is still a root. It's just one that appears 4 times. 4 minus I is still a root. It just appears 7 times. You could say all those things. But by me saying no, it's got to be of lowest degree, that means don't get fancy with the multiplicities. It's got to be a polynomial. If we fully multiply this out, it's going to end up being a 3rd degree polynomial. If we had put those powers on it, that would make it a much higher degree polynomial, specifically an 18th degree. So we're not going to do that. We're going to keep it simple as we can. I think it would be helpful real quick if we multiplied this out, which means we need to do all these roots multiplied together and simplify. I'm going to start with this one here because these are conjugates. And it's going to make for some cancellation. So I'm going to FOIL it out. We're going to get x squared minus, this time I'll put the x first. So I'm doing x times x times -4 plus I, and then minus 4 minus I times x. I'll put the x first again. I'm going to run out of space. And then I'm going to have plus 4 minus I times 4 plus I. Like that. Now I need to simplify this business even more. We get x squared. I'm going to distribute this minus x here. Minus 4x minus I times x. Now I'm going to distribute this negative x out. So minus 4x plus I times x. Then I need to FOIL out these pieces here. 4 times 4 is 16, plus 4i, minus 4i, minus I squared. Let's clean that up a little bit. And now we can do some of our simplification. We've got minus ix plus ix plus 4i minus 4i. This becomes minus I squared. I squared is -1. So it becomes plus 1. We already had plus 16. We still have minus 4x. We still have another minus 4x. And then we have the x squared at the beginning. And now we just got to combine like terms here. X squared minus 8x plus 17, 16 plus 1. So altogether, this polynomial is going to become x plus 2 times x squared minus 8x plus 17. And now to fully finish this off, we need to multiply this x plus 2 out. We need to distribute it out. So this is like extending FOIL. We do the x times everything in here. We do the x times that, times that, times that. We do the positive 2 times that, times that, times that. And now you can see why these get cumbersome. It's not necessarily difficult what we did. The only real new thing we learned here was that we have to include the complex conjugate of 4 minus I as a root here. That's all we learned new. This is just kind of the tedious work we have to do, the heavy lifting we have to do. And it's not fun. So multiplying the x through, you're going to get x times x squared, which is x cubed, minus 8x squared, plus 17x. Then you distribute the positive 2 through, you're going to get plus 2x squared, minus 16x, plus 2 times 17 is 34. And now all we need to do is combine like terms. The x cubed is all by itself. Minus 8x squared plus 2x squared, those are like terms. Negative 8 plus 2 is negative 6. Plus 17x minus 16x. 17 minus 16 is just 1. So it's just plus x and then the plus 34 at the end. Whew. And we're done with that one. So this is a polynomial that has this thing down here, this cubic polynomial, has roots of negative 2 and also 4 minus I. It also has a root of 4 plus I, and it has to have that as a root. And it's of lowest degree. It's a third degree polynomial. You can't go any lower than that because you have to have at least 3 separate roots in order to achieve everything here. Whew, that one's in the bag. Finally, the very last thing about this section, I'm going to have you look at a very simple rule on your own. Look at Descartes' rule of signs on your own. It won't be on any tests. There won't be any questions over it on a test. There may be 1 or 2 quick homework problems that cover it, but that's 1 or 2 problems in a sea of greater things, and Descartes' rule of signs would take about 30 minutes just for me to lecture over, to teach it all. So, you know, we just don't have that kind of time for something that's very minor and is not even going to be on any tests. We have more important things we need to cover. Speaking of which, we are done with that section. So give yourselves a pat on the back. We're done with the longest section in this entire course, and it took pretty much all of last class and most of today's class to cover. And that's just how it is, kids. There's no way around it. It was just nasty and filled to the brim with yummy goodness. So in this next section, we're going to talk about the graphs of polynomials. And this section is actually kind of interesting. It's really interesting to me because a lot of what we're going to be introducing here can be derived if we just kind of think about it and we use a little bit of logic. Now, it's not easy per se, but it's not exactly going to be something that you couldn't just reason through. And that's why I really like this section. Look, there's a lot of things in math where it feels like they're just thrown at you. And that is partially true. It doesn't mean they're not based on something. It just means all the finer details of it take a lot. It takes a lot. So real quick, let's recall the degree of a polynomial is the highest power. So that last polynomial we did that we fully multiplied out, that last nasty problem, that was a third degree polynomial because it was the highest power was 3. Also recall the lead coefficient, which henceforth I shall dub the LC of a polynomial. That is going to be the coefficient of the highest powered term. It's only the leader, it's only at the front if the polynomial is written in descending order. Meaning you take the highest powered term first, then the next highest power, then the next highest power, all the way down. But it's always going to be the coefficient attached to the highest powered term, even if it's not written in the lead. That's kind of confusing, I admit. We'll look at a few examples to remind ourselves. First, let's look at an example that is written in the preferred descending order. Oh, how about 17x to the 6th minus 9x to the 4th plus 12x cubed plus x. So it's missing a few terms. It's missing a 5th degree term, a 2nd degree term, and a constant. But that's fine. It doesn't have to have them. You could just say those coefficients are 0 on those terms. So the degree here, well, it's written in descending order. The highest powered term comes first, and then it just goes down the line. So the degree is really easy to figure out. It usually is anyways. The degree is 6. It is that highest powered exponent. The lead coefficient, which I promised would just be called LC, is going to be the coefficient of the highest powered term. Now it happens to be in the lead here because we have it written in the proper descending order. So the lead coefficient is 17, which is a positive number. However, you know, they always talk about the real world whenever you're learning things in school. In the real world, you know, you're not always going to see that highest powered term come first. It's nice when it's the case, but it's not guaranteed. So let's look at another example. This is going to be more of a real world example. You could have something that's just kind of slipshod and put together here. How about negative 13x to the 4th minus 9 plus 12x cubed minus 910 x to the 19th power. Whew. This polynomial is not written in descending form because if it was, this would be the highest powered term and it would go first. And then the 4th degree term, then the 3rd degree term, then the constant. But that's okay. We still have to recognize that the degree of the polynomial is 19. It's the highest power you see. We also have to recognize that the lead coefficient is not the first coefficient you see. It is the coefficient of the highest powered term. It's negative 910, which is a negative number. Now you might be thinking, okay, I get this point. It's not a particularly difficult point. And maybe I would agree, but sometimes when you're on an exam You've got a lot of things flying at you. You've been maybe a little bit stressed out. Your mind is just kind of going off in a million different directions. You might be tempted to just think of the word lead and think it's got to be the thing that's in front, the leader. And generally speaking, I always make this joke. One of you will betray me and you will call this the lead coefficient, the negative 13 here, and you will have been tricked, but it's probably just due to exam stress. But just keep that in mind. That is something that we're going to need to remember. So now that we are refreshed on what is the lead coefficient and what is the degree of a polynomial, now we need to really start talking about the way that a graph will look of a polynomial. And we start by talking about something called the end behavior test. This describes what the graph of the polynomial will do as you go all the way to the left, which is negative infinity, and also all the way to the right, which is just positive infinity along the x-axis. In other words, what will the polynomial do if I take a simple graph and I graph the polynomial, let's make it green, and I go like, woo, and it won't quite be that straight, but whatever. The lead coefficient test is interested in what does the polynomial do as I go along the right on the x-axis. In this case, this polynomial blows up to positive infinity. Blows up, I should say. It blows up to positive infinity and it goes up and up. And as I go to the left, as I go down to negative infinity along the x-axis, this thing falls. It falls down to negative infinity along the y-axis. So positive infinity on the x-axis also goes up to positive infinity on the y-axis. It blows upwards. That's going to be what the end behavior test is concerned with. So the end behavior test is going to look at two characteristics of the polynomial, and just from looking at those characteristics, I can tell you immediately what is it doing to the right and what is the polynomial doing to the left. I can't tell you what it's doing in between. I can't tell you what's going on in the middle stuff, in the goodness here. That's going to be something we'll do next. But I can tell you, just using the end behavior test, what it's doing. So the first thing that can happen, and that's a terrible arrow. That isn't much better, but it's going to have to function here. A polynomial that goes to positive infinity to the right and also positive infinity to the left. You might say that this rises right and rises left. You might say that's the case. That's only going to happen if we have an even degree positive lead coefficient. I'm going to move this just a hair to give myself a little space here. It's going to rise to the right, go woo, blow up to positive infinity as I go along to the right. Also blows up to positive infinity as I go along to the left. So you look at the degree of the polynomial. The degree has to be a positive integer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. If that degree is an even number, 2, 4, 6, 8, 10, 12, etc., and the lead coefficient is a positive number, this is what it's going to do. Now, what is it going to do in the middle with Malcolm? I don't know. I can't exactly say just from knowing these two facts, but I can tell you what it does to the right and to the left. So suddenly you can imagine 4 different possibilities. Even degree positive lead coefficient, even degree negative lead coefficient, odd degree positive lead coefficient, odd degree negative lead coefficient. And that's exactly right. Those are the 4 principal elements of the end behavior test. All right, let's use a different color. You also have the case where it falls to the left and also falls to the right. So you might call that falls right, falls left as well. Again, I don't know what it does in between the ends, if so to speak. But this is going to happen whenever you have still an even degree, but now a negative lead coefficient. So even degreed polynomials, they go in the same direction with each other. Either they both rise, they both go up, or they both go down together. And now just to make it look the way I want, I need to know, hey, you just delete that. Well, you know what? Never mind. Life will just have to go on. I was going to make this part green just so it's not an eyesore, but I guess it's content to be an eyesore. Okay, so now the other possibilities are that they go in separate directions. That's going to occur when you have an odd degreed polynomial. Schma. So you can have this occur. The first thing the way you can do it is if it rises to the right, but falls to the left. So rises to the right, falls to the left. This will happen when you have an odd degree, but still a positive lead coefficient. And then there's one more case. We'll draw it out just for completeness sake. Go up here. How about orange? This one's going to rise to the left, fall to the right, so falls right, rises left, and that is going to occur when you have an odd degree and a negative lead coefficient. Okay, so kind of interesting stuff. This is called the end behavior test. There's a reason it does this. There's a reason it does this. It's not always the easiest to describe just verbally. But basically, think about when you have an even degree and a positive lead coefficient. If you have an even degree, so like the highest power is 2, 4, 6, 8. That's the highest powered term. So while all the terms after it can do all kinds of wonky things, the highest powered term really is the most revealing about what this thing's going to do in the extreme. As I go to positive infinity along the x-axis, as I go to the right, if I have an even degree, I'm taking these x values and they're getting larger and larger and larger. They're being then raised to an even power, so then they're getting even larger. And then it's a positive lead coefficient, so the numbers are staying positive. As I go to the right along the x-axis, all of the x values are just getting larger and larger and more positive. As I go to the left on the x-axis, since it's an even degree, we'll think about what a second power does. If you plug a negative number into it, the second power makes it positive. And since that degree then, if because it's even, it's always going to make negative numbers positive. So as I get more extreme, as I put in smaller and more negative x values, they're actually becoming positive because of the even degree, and the lead coefficient is positive. So it's only reinforcing that. So as I go to the left, it's only getting more and more, it's only getting larger and larger and more positive. And so that's kind of what it's doing. Now, along the middle, it could fall below the x-axis. In fact, it should in most cases. Now think what this is doing. This has an even degree, but a negative lead coefficient. So as I go along here, I'm getting more and more larger values, but then they're getting smacked by a negative lead coefficient, and they're coming down and becoming more and more negative, actually. And it's following that pattern over here. For an odd degree polynomial, as I go to the right, these x values are getting more and more positive. And since they're getting hit with a positive lead coefficient, they're going to stay positive. But as I go to the left now, I'm plugging negative x values into the polynomial. When they get hit with an odd degree, they stay negative. They become negative y values, and the positive lead coefficient doesn't change their sign. So that's kind of what's going on here. That's a good, quick verbal description of the process that is happening here. And then you can reason similarly for this last one. So the end behavior test is a major component of us finally being able to graph some of these polynomials. The other thing that is going to affect this is the multiplicity. Let's use a different color. Let's use black. Multiplicity of a root. This will affect what the graph does at the root itself. This is going to affect that. Basically, what's going on let's say you have a graph, a polynomial, and I'm just going to kind of make one up here. It's going to do something like this. Let me freehand it real quick, actually. It'll look a little smoother. Let's say it looks like this. It's a little sharp right here. Imagine it was just a little smoother. My finger kind of came off the screen. Imagine your polynomial is doing something like this. Now here, it crossed through the x-axis, which is what it usually does. That's the usual thing we expect it to do. It went from one side of the x-axis and it completely crossed through it. which is different from what this one did. This one came down, gave the x-axis a little kiss, and then went back on its merry way. So whenever you cross through the x-axis, whatever that root was, the root here has an odd multiplicity. So odd multiplicity goes hand in hand with straight up crossing completely through the x-axis. When you just touch the x-axis, just touching touches the x-axis, but continues along its merry way. That's what this one did. This root has an even multiplicity. And that's going to be true in general. Now, again, the reason it does it is a little bit kind of difficult to explain verbally. But basically, when you have an odd multiplicity, as you come from the left, negative numbers then get applied to an odd multiplicity, and they stay negative. Positive numbers stay positive. So negative switches over to positive as the x values do the same. But here, with an even multiplicity, negative x values become positive, and then as you go to the right of it, positive numbers stay positive. So even multiplicity means that you're going to stay one way on either side. Again, that's not a great description of why. Unfortunately, this for now is something you may need to commit to memory. Frankly, we'd have to have more time for me to really show an example of why it makes sense that this does that. So if we wanted, let's say just for kicks, that the x value here, the root, has an x value of 3. And then let's say right here, this root has an x value of negative 4. Well, if we were to write the function, if we were to write out the polynomial in factored form, well, a root of negative 4 is really a factor of x plus 4. Remember, we flip the sign when we write it as a factor. So we would have x plus 4 as one factor.
Good morning. Please excuse the interruption. Today is Senior Retake Picture Day. You will be taking pictures in the library. There is a sign-up sheet on the library door. If you have already signed up, please be sure to record for your picture at the appropriate time. If you need senior retakes and you have not signed up yet, you must come down and put your name on the sheet during this coming passing period. Seniors that are taking your pictures, please remember you must have appropriate garments in order for your picture to be taken. If you have questions, please come by the office. Thank you.
Picture day. I remember picture day. Picture day was always fun because they would make the mistake of telling you it was picture day in advance so you could look nice. So, that's when, all my friends and I, we would make little pranks or we'd wear some really dumb shirt. And we were very proud of it. And we always liked making the photographer's life just not fun when it came to us. Of course, now when I look back on it, I realize I really desperately needed attention. I needed people to laugh at me and laugh at my jokes. So picture day was probably not good for me in the long run. And no one ever really disciplined me for it. They're like, oh, that Josh, he's a funny guy. But they probably should have laid the hammer down on me for it. Anywho, so this is the factor x plus 4. Then we have a factor x minus 3. Yes, those are going to be factors here. But their multiplicity, the number of times they appear, Well, x plus 4 has to appear an odd number of times. So it could have a multiplicity of 1, which means you don't really even need to write anything. But it could have a multiplicity of 3, 5, 7, 9, 11, etc. And then this has to have an even multiplicity. So this needs to be squared, or it needs to be to the 4th power, etc., 6th power, 8th power. That's basically what's going on here. What's interesting also is that you can tell from the end behavior test that this thing falls to the left but rises to the right, which means that the entire degree of this polynomial must be an odd number because they're going in opposite directions, and it has to have a lead coefficient because it's rising to the right. So just kind of an interesting thought to keep in mind. Of course, with it written like this would be, add 3 to the degree. This would add 4. So there'd actually be a degree of 7 here if we took this polynomial as it's written. This would have a degree of 7. And then it would have a lead coefficient just because the implied number here is just a 1 in the very front. And if you were to multiply it all out, you would see that the lead coefficient also just kind of stays positive here. So the end behavior test can give us an idea of what the graph does on the extreme ends as I go all the way to the left and as I go all the way to the right. That's what the end behavior test tells us. The multiplicity of a root tells us what the end behavior does at an actual root, or not the end behavior, I'm sorry, what the graph does at an actual root. Does it fully cross the x-axis, or does it merely touch it and then go back along the way it was along its path? Well, the problem is those two things are very important. Those are valuable, but even that doesn't tell us everything because we still have to figure out what those roots are. We still have to figure that out. If I gave you the function, the polynomial, 2x cubed, and I'm going to need more room. So easy to get carried away here. I'll just write it all the way down here, fine. If that's where we got to do it. 2x cubed minus 3x squared minus 18x plus 27. If I gave you that polynomial, well, there's some good news. I can tell you what the end behavior is. Oh, it's an odd degree, positive lead coefficient. So it does something similar to this. It rises to the right and falls to the left. I can tell you the end behavior, but I really can't tell you a whole lot else until I factor this. I'm going to need to factor this. I'm going to need to figure out what the roots are based on the factors. I can also tell you what the multiplicity of those factors are once I've fully factored it. And so then I can fully do it. So the end behavior test is only one part of it. We still are going to have to factor these polynomials. In fact, you could even argue that's the whole reason we went through the song and dance of that last section. That last section gave us the tools to factor. So basically, we still need to factor this in order to really be able to graph it and get a full picture of what's happening.